Hello friends, today's question. A solid sphere of radius r is floating in a liquid of density ρ with half of its volume submerged. If the sphere is slightly pushed and released, it starts performing simple harmonic motion. Find the frequency of these oscillations. So we are given a sphere which is floating in a liquid. This is a liquid. And we have a sphere, and it says that half of its volume is submerged. So we have this sphere of radius r and half of its volume is submerged in the liquid, and then it is pushed a little bit in the downward direction, and we say that let the amount which is pushed in the downward direction is, let us suppose, is x. So it is pushed a little bit in a downward direction by a distance of x. So you can say into two parts. This is our initial condition, and this is our final condition. So initially there will be two forces acting on this sphere. First will be the buoyant force acting in upward direction. Let us call that Fb. And the second one will be the weight of the sphere that will be acting on a downward. Let us suppose that we call as W. And initially it said it is in equilibrium, so both these forces will be equal. And in the second case, we are going to make once again use of the you can say buoyant force concept, and find out the amount of the water that is displaced when this sphere is pushed by a distance of x in the downward direction. And then we are going to form the equation, and we are going to get the result for the frequency of the oscillations. So you can say for initial condition, can say at equilibrium buoyant force is equal to the gravitational force acting on the body at equilibrium buoyant force is equal to the gravitational force acting on the sphere. And we are going to find out the volume of the sphere, and we are then use that it said in the question that the volume is only half is submerged. From that we are going to find out how much volume of the water is being displaced, and that is going to give us the amount of the buoyant force. So we have volume of sphere, let us call that V, which is 4/3 pi r cube, and it is given that only half is submerged in the liquid. So we are going to find out amount of water displaced by the half of the volume. Okay, since the sphere is half submerged, the volume of liquid displaced, the volume of liquid displaced, let us suppose that is given as V displaced, which is equal to half of V, and we get this as 4/3, and we have pi r cube. and the gravitational force is nothing but the weight with which weight of the sphere. So therefore we can say that the weight of the sphere will be equal to mg, where m is the mass of the sphere. And if Fb is the buoyant force, so you can say buoyant force on the sphere called as Fp, then Fp will be equal to density of the liquid is given as rho multiplied by volume that is displaced and acceleration due to gravity. And at equilibrium, this buoyant force will be equal to mg. At equilibrium, Fp is equal to mg. So we substitute value of Fp. Fp is our rho V volume of the water displaced multiplied by G is equal to mg. G and G cancel out, and we substitute value of water volume displaced. So from here we get m is equal to rho multiplied by half, and that is 4 by 3 pi r cube. So this is the mass of the sphere, okay, with respect to the amount of the liquid that is being displaced by the sphere. Now we assume that a small x is the sphere is displaced by the small distance, displacement is x in the downward direction. So because of that, there will be storing force acting on it. Let us discuss the storing force for the small displacement. Storing force for small displacement, which is taken as x. So we can say the sphere is displaced slightly downwards by x. The additional volume of liquid displaced is proportional to x, is proportional to x. So therefore we can say the change in the buoyant force, the change in buoyant force, which is, let us suppose, is given in delta Fp, and this will be equal to rho density of the liquid, area multiplied by x, which is giving us a volume, and multiplied by G, and where A is the area of cross section for the sphere. A is the area of cross section, and that will be equal to pi r square. Okay, because when the cross section is cut for a sphere, from the top side it will be giving something like a circle, something like this. Okay, so this is our radius r. So the area of cross section will be our A, because the displacement is very small. Okay, so this we can be treated as a, instead of a sphere, we can treat this as a circle, small thickness. So this will be pi, not linear to for the need not to go for the complete, you can say, complete thickness of the sphere. So from here we can write that delta FP will be equal to rho, and we have here pi r square multiplied by x multiplied by g. So now we can write the equation motion for the SHM. Equation of motion for SHM. So net restoring force on the sphere when it is displaced by x, let us suppose, is given as F restoring, and that will be equal to density of the liquid multiplied by the area x as well as g, but we will do in the opposite direction, okay, because the restoring force will be provided by this change in the buoyant force. So you can say net restoring force acting on the sphere when displaced by x. And let us suppose that is given as Fs, which will be minus rho pi r square x multiplied by g. And now we can use the Newton's law, which restoring force is equal to mass into acceleration. Using Newton's law, Fs is equal to mass into acceleration, and which can be written as mass into double derivative of this x with respect to time. We substitute here, we get this as m double derivative of x with respect to time is equal to minus rho pi r square x multiplied by g. And we already calculated what will be our mass for the that sphere. Okay, so this is the mass of the sphere. So we substitute here, we can write double derivative of x, and mass was our rho multiplied by half and its volume, that is 4 by 3 pi r cube is equal to minus rho, we have pi r square x multiplied by g. Rho cancel with rho, pi goes with pi, and this square goes with this, so r is left here. So therefore, and this also goes up 2. So we can write this as double derivative of x with respect to time is equal to minus 3 by 2, and we have g upon r multiplied by x, and this is nothing but equation of SHM. So from here we can write our omega, or we can say omega square is equal to 3 by 2 g upon r, which gives omega is equal to square root of 3 g upon r, or we can say our frequency, which is omega upon 2 pi is equal to 1 upon 2 pi, and here we have square root of 3g upon 2r. So this was asked for in the question, that frequency of the oscillations. So this is frequency of oscillations. So this completes the question. Thank you.